right, here we go. Lesson 2-4. Alright guys, here we go. Instantaneous rate of change. Okay, so today we're particularly going to hit a lot on velocity, but all of the problems we do will be talking about an instantaneous rate of change. So that is different from average rate of change because you're finding the change at a particular moment. Okay, so we've discussed instantaneous rate of change as the derivative of a function at a particular value. Average rate of change is this. What is that? Average, what do we use? Slope formula. This is the same as y2 minus y1 over x2 minus x1. So that's just a fancy slope formula. Okay. All right, instantaneous rate of change is when we take that same thing and take the limit as h approaches 0. So that was that long method that we used to find the instantaneous rate of change. Okay, so instantaneous is often used when x represents time, but it is also used for situations that do not involve time. When we were asked to find the rate of change, it should be assumed that instantaneous is implied unless otherwise noted. Okay, so find the rate of change of the area A of a circle with respect to its radius. Okay, what is our formula for area of a circle? Pi r squared. Okay, so for part A, we're going to take our formula, A equals pi r squared, and remember that pi is just a number. It's not a variable. Right, even though it's a Greek letter, it's not representing a variable there, it's representing a constant. Okay, so we are going to take the derivative of this with respect to r. Okay, what's the exponent of r? We're going to bring it down and multiply it by the coefficient that's already there. So 2 pi r to the 1, which is just 2 pi r. And do you know or recognize that formula? Circumference.
So the circumference is the derivative of the area?
Mm-hmm. So the rate that the area of a circle is changing is the same as the circumference of it. All right, pretty cool. Okay, part B says evaluate this rate of change of A at r equals 5 and r equals 10. Okay, so at r equals 5, how fast is this area changing? I would just plug in 5 for r, and I would get 2 pi 5, which would be 10 pi. And I don't think we had any units of measure up here, did we? We did not. So when you're not given units of measure, you just don't provide any with your answer. Okay, then when the radius is 10, the rate of change would just be 2 pi 10, which would be 20 pi. So we doubled the radius, we doubled the rate of change that the area is increasing, which kind of makes sense. As the radius increases, what happens to the rate of change in the area? It also, which makes total sense. The appropriate units for dA over dr are what? Maybe I did give? Oh, okay, we need to read C first, my bad. If r is measured in inches and A is measured in square inches, what units would be appropriate for dA, dr? Okay, so if this circle radius is in inches, what units would area be in? Inches squared or square inches. Okay, but then over radius, and the radius is in inches. So square inches per inch. Would I reduce that to inches?
Yeah.
Oh, would I multiply them?
Or you could just find the derivative and do what you have.
But those aren't numbers, those are just units.
I really think it's
Okay, it is kind of a trick question because think about if I reduced it and I said just inches. That's like a ruler kind of measurement, right? That's not comparing how your area is changing with respect to the radius.
Sine squared the same. I mean, sine the same as sine squared over sine.
It is. Yes. So normally, like if this was an x squared over x, yes, I would reduce all day long. But in this case, I maintain that and don't reduce it because I want it to represent change in area per radius. And if I reduce it, then it just becomes like a radius measurement. So we actually would not reduce it because if we reduce, we would have as our unit. Okay, so we keep it square inches over inches to maintain the comparison of area to radius. Otherwise we lose that, because per really means divided by. It means you're comparing something. So if we lose that, then it has no meaning as to how the area is changing with respect to the radius. Okay? All right. If we had just inches, then that's linear, right? That's clearly not linear if we don't reduce it and keep it as a comparison. Okay. Next, motion along a line. Okay, suppose that an object is moving along a horizontal axis. We're going to call it the S-axis, so that we know its position S on that line as a function of time t. S equals f of t, so position is a function of time. The displacement of the object over a time interval t to t plus delta t is the change in position over the time interval. Displacement equals final position minus initial position. Okay, so think about a number line. Let's say, okay, so let's say that I start at 1. And then I move to the right and end up here at 4. What is my displacement?
4 times 3.
Okay, is it negative 3?
No.
No. Okay, but what if I started at 4 and stopped at 1? Then it's negative 3. Okay, so the difference being where you started and where you stopped in relation to each other. So that's what this means. Displacement is where you stop minus where you started. So if I started at 1 and ended at 4, the displacement would be 4 minus 1, or 3. But if I started at 4 and ended at 1, then it would be 1 minus 4 would give me negative 3. Okay, so can displacement be negative? Yes, it just indicates that you stopped to the left or below, whichever direction we're calling negative, of where you started. Can displacement be 0?
Yeah.
Okay, what if I start at 1, I go to 4, I drop back to 2, I go to 5, and come back to 1? What's my displacement? 0. Does that mean I didn't move? Absolutely not. It just means I stopped where I started. Okay, so S equals f of t is just a generic way of representing a position function. Change in S is your displacement. And then what does this t plus delta t mean? Time plus change in time. Okay, so just how much time you were moving or whatever you're doing. In this case, we're just moving. All right, so displacement is final position minus initial position. Final position could be written as S plus delta S. minus s. What does that mean? What's delta s? Change in position. Okay, so it's the same thing as where you ended, final position, minus initial position. It's just fancy letters to represent where you stopped minus where you started. Okay, so look at this fancy equation here. Delta S, change in position, displacement, is the function evaluated at time plus change in time minus the function evaluated at time. Same thing, final position minus initial position. Final position, initial position. So it's saying if I want to find my initial position, then I put my starting time into the function and I evaluate it. Okay, average velocity. What do you think that means? Average. Displacement average travel time. So that is kind of like your average rate of change that we have been doing. So that's like a y2 minus y1 over delta time, change in time. How do you think we would find the instantaneous velocity or the velocity at one specific time? Put what? What'd you say? I thought you said it right. Yes, plop the limit right in front of that thing. So we're going to say, okay, well, let time be practically 0. And then we can figure out how fast we were going. We were changing position at this particular time. Not from time 1 to 5, but from time 1 to 1.00001. So that would give us an instantaneous velocity. Okay, so we are going to take the limit, just like we did before, of average velocity. Okay. All right, so here is our official definition of instantaneous velocity, putting all of that we just talked about together. V of t, why do you think I'm using V? Velocity. Velocity at a given time is your change in position over change in time. So it's the derivative of your position function with respect to time. And here's our old, long definition of derivative right there. Okay, so bottom line is velocity is the derivative of position. Okay, but that makes sense because velocity, let's say we use miles per hour. That describes a change in distance, miles, per time, hours. So that would be a derivative of position with respect to time. Miles per hour, feet per second. Mm-hmm.
So we've been doing the derivatives in class. That's finding like the average change.
Average.
Or would it be like, or we find like the
instantaneous is derivative. If anything says find the average rate of change, then that's straight up slope formula.
Okay, so this stuff we would just find the derivative.
Yep, instantaneous. So if I want to know how fast I'm moving at a particular moment, then I find the derivative of the position function, plug in that time that I'm interested in. Okay, just like the lines we were working with just a minute ago. Okay, velocity versus speed. A lot of people use those two words interchangeably. And in general, it's pretty accurate, but technically it's not. Okay, besides telling how fast an object is moving, velocity tells the direction of motion. So when the object is moving forward or in S position is increasing, the velocity is positive. When the object is moving backward or position is decreasing, velocity is negative. So if I walk backwards, that's technically a negative velocity. Suppose we drive to a friend's house. Distance from home is increasing, positive velocity, and our speedometer shows 50 miles an hour. When we return home, distance from home is decreasing. That is technically negative velocity. But our speedometer will not show negative 50 miles an hour, will it? Okay, so the speedometer is showing speed, not velocity. Speed is the absolute value of velocity. Speed is always positive. Speed measures the rate of motion regardless of direction. Okay, so that's why it's called a speedometer, not a velocityometer. Because velocity can be negative. Speed cannot be negative. Okay? All right, so definition of speed is the absolute value of velocity. So speed is the absolute value of v of t, or the absolute value of the derivative of position with respect to time. Okay, so speed is always positive. Velocity may be negative. All right, we ready to do our brain in reverse? This is one of those reading a derivative graphs. Oh. Okay, reading a velocity graph. Okay, so this graph represents velocity. The y value is velocity. The x value, or the horizontal, is going to be time. I think we're going to get units in just a minute when we read over here. But it says a student's velocity graph from data recorded by a motion detector is what we're looking at. A student walks around in front of a motion detector that records her velocity at 1 second intervals for 36 seconds. Okay, stop right there. This is time in seconds. If this goes from 0 to 36, how much is each tick mark? Like or exactly? 4? 1, 2, 3, 4, 5, 6, 7, 8, 9. Into 36 is 4. So let's mark that. 4, 8, 12, 16, 20, 24, 28, 32, 36 seconds. She stores the data in a graphing calculator and generates the time velocity graph that is shown. Okay, were we given any units for distance? Of course, her velocity, we were not, were we? All right, what do you want to go with? Meters? We're just going to assign meters. Since she's walking, it's more likely meters. Okay, look at the y-axis. What is the scale here? For the whole thing, so each tick mark is 1. Sophia, you good?
Really, that doesn't look like a 0.5. That looks like a 0.8.
I agree, but we have to go by what's given down here, so we're just going to have to buy into that. Okay, so we're going to answer these questions. What is X representing? Time in seconds. What are the units for X? Seconds. Okay, what is Y representing? Velocity. And what are the units? I didn't quite finish up at the top. Meters per second. And we made up the meters part. Didn't I actually say that? Okay, per second. Use the graph to describe her motion as a function of time by reading the velocity graph. And then at the very end, we're going to figure out when is her speed at a maximum. Okay. All right, so let's interpret this. This right here represents positive values. right? The y values are positive. That means that her velocity is positive. If my velocity is positive, what does that mean? She's going in a what direction? Positive direction. Okay. What if she's moving in front of a motion detector? I don't know. Maybe away from it would be positive. I'm just going to say positive motion. Usually it will say either up or right is positive, but with this motion detector, I'm not sure. So we're going to say she is moving in a positive direction from when to when? Okay, I'm going to say on, and I'm going to write an interval, 0 to 14-ish, okay? What happens right here? Okay, the graph crosses the x-axis. What is she doing? She's what? Stopped. Because what is her velocity? 0. Okay, all right. Important point right there. Velocity is 0. That means she stops. So I'm going to use a parentheses on 14. Okay, she stops at approximately t equals 14 seconds. Okay, she is worn out. She's tired. She needs to stop and rest. I know, bless her heart. Okay, so now we've got all these velocity values that are negative. What does that mean about her motion? She's moving in a negative direction. Is moving in a negative direction on the interval. Okay, so it's going to start right after 14 seconds until when? About 26. Okay, what happens at 26? Velocity is 0. But look, it's 0 that whole span right there, isn't it? Okay, so what happens? She is just resting. Okay, Bronwyn?
Okay, so, like, you know how part of the graph, like, goes down?
Right here?
Yeah, or, like, at the
here?
positive part, whatever it's going.
Uh-huh.
If it's describing like she's walking forward, like, what does it mean whenever the steep is going?
Okay, all right.
Like, whenever it starts to
Okay, good question. So all of this is positive here. So she is moving in a positive direction, but think of this as speed. Remember I said they're not exactly the same, but velocity is positive here, so in this case it would be the same as the speed. Okay, so she's walking 1 meter per second, 2 meters per second, 3 meters per second, so she's walking faster. And here she's maintaining the same speed, and then she is slowing down, but still walking in a positive direction. But her pace is slower. And that makes sense because she's coming to a stop. So if you come to a stop, you have to eventually slow down. Yes. Maybe she's an Olympian.
I disagree.
Okay. All right, let it be noted. Maybe she's receiving a medal right there. All right, so she stops to receive her medal from 26 to when? 32-ish? Okay, then what does she decide to do after that? Man, there she goes again. She is Speedy Gonzales there. She is walking in a positive direction again because her velocity is positive.
So what caused that little turn?
Okay, hang on. Let me write this down and then I will answer your question. She is moving in a positive direction again from 32 to 36. And I'm just going to use parentheses because I don't know. If she stopped, it would have to come back down to the x-axis, right? Mm-hmm. Okay, so Bronwyn, question.
That little turn in the negative portion.
Here? Yeah. Okay, so what is she doing there? Okay, so this whole time she's walking in a negative direction. So maybe think of it as back towards the camera. Okay, but she's picking up her pace and walking faster, but then she's slowing down at a slower pace before she stops. Okay, so think of it as reading these actual numbers. She's walking 7 meters per second. Here she's walking 3 meters per second. Here she's only walking 1 meter per second. So she's coming back towards us, but slowing down as she gets closer. Mm-hmm. Demonstration. You know what? I think we are going to demonstrate this in a minute. On, wait. I think that this is, yes, we're going to do a similar demonstration on the calculator.
No, I want a real life demonstration.
All right. When is her speed at a maximum? When is her speed at a maximum?
14.
It is the absolute value. So when is it at max? 20? Who said 20? All right. Why 20? Because that is when, look at her velocity there. It's like -7 meters per second, but what's the speed? 7. Up here, it never gets above 4-ish. So her speed is greatest at t approximately equal to 20 seconds. Question. All right. Okay, so acceleration then. The rate at which a body's velocity changes is called the body's acceleration. Acceleration measures how quickly the body picks up or loses speed or velocity. Rate of change means derivative, right? So our definition of acceleration is that it is the derivative of velocity. If a body's velocity is ds dt, then the acceleration is the derivative of velocity or the second derivative of position. Okay, so acceleration is the derivative of velocity, which is the second derivative of position. So it's how your velocity is changing. Alrighty, so a few things to summarize here. Position. We often use S of T. I don't like that, but we do. Units are things like feet, meters, miles, inches, etc. They're distance units. If we're measuring velocity, which is the derivative of position, then those units are some distance over some time, like feet per second, miles per hour, meters per second, etc. And then acceleration, which is the derivative of velocity, or the second derivative of position, units are a distance per time, because it's velocity per time. So it's things like feet per second squared, meters per minute squared, etc. Okay? All right, the earliest questions that motivated the discovery of calculus were concerned with velocity and acceleration, particularly the motion of freely falling bodies under the force of gravity. The mathematical description of this type of motion captured the imagination of many great scientists, including Aristotle, Galileo, and Newton. Experimental and theoretical investigations revealed that the distance a body released from rest falls freely is proportional to the square of the amount of time it has fallen. We express this by saying that position is 1/2 gravity time squared, where s is the distance, g is the acceleration due to Earth's gravity, and t is time. The value for gravity depends on the units used to measure s and t. With t in seconds, which is our usual unit, we have the following values. You may have seen these different numbers in your science classes. If we're dealing with feet per second squared, then gravity is falling or pulling at 32 feet per second squared. But if we're using meters, then we use 9.8. So it just depends on the problem, the situation that we're in. We will use both of these from time to time. So you'll see this 16t squared and 4.9 t squared. We've used both of those already in here. And of course the 16 and 4.9 are coming from the 1/2 times the gravity. Okay. Alrighty, next page. Modeling vertical motion. Ooh, this is a good one here. A dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second, which is about 109 miles per hour. It reaches a height of x equals 160t minus 16t squared after t seconds. Instead of s, we're using x here. So this is our position function, because it's height. It's measuring the height, so that's the distance that this rock is reaching. Part A, how high does the rock go, and what is the time when this height is reached? Okay, picture what's happening up here. Is time going to be negative? No. Okay, so it's blasted, it goes up, but what happens? Then it comes back down, and it should be parabolic in nature. Okay? So it will eventually reach a highest point, and at that highest point, time should be halfway, because we're not dealing with like wind or friction or anything like that. We're just keeping it simple. So halfway during this path, it reaches its highest point, then it comes back down. Okay? If this is a parabola, then we call that the what of the parabola? The vertex. So that vertex will be important. Do you remember a formula for vertex? Okay, we might need that. We'll see. How high does the rock go, and what is the time when this height is reached? How am I going to do this? Yeah, we need to know both. So the time will be dependent, or I should say the height is dependent on the time, right? Okay, think about what we've been dealing with lately, derivatives. When I reach the top, what's the derivative? What's the derivative at the top of that hill? What's the slope of that tangent? Zero. So if I could find where the derivative is 0, I would know the vertex. Okay, that's an easy thing to find a derivative of, isn't it? Okay, so I want to figure out when is velocity, which is going to be x prime, velocity, 0. And then once I know the time, then I can find the height by plugging it into the original equation. Okay, so I'm going to take my derivative. Velocity of time, with respect to time, is 160 minus 32t. And if I set that equal to 0, that's a little baby equation. And what is t? 5 seconds. Okay, so now I know it took 5 seconds to reach this highest point. So I know that that time is 5. Do I know when it reaches the ground again?
Yep.
When? 10. Goes up 5, comes down 5. Okay, so now that I know it took 5 seconds to reach the highest point, I can find the highest value by doing what? Plugging 5 into the position function. So I'm going to find x of 5 is equal to 160 times 5 minus 16 times 5 squared. What if I got a negative here? Would that be okay?
Negative 5?
My time is 5. What am I finding?
Oh,
The height. So would negative be okay? No, we're not going underground, right? 400? 400 feet. Oh, meters, feet. What is it? Meters. No. Feet. Okay, so at 5 seconds, it reaches 400 feet. Part B. What is the velocity and speed of the rock when it is 256 feet above the ground on the way up and on the way down? Okay, if it reaches a height of 400, then somewhere on the way up, it reaches 256, right? So 256 here and here. On the way up, on the way down, it will go through 256 feet. I want to know what the velocity is here and the speed. To find the speed, I have to find the velocity first. How do I find the velocity there?
Plug 256 in for x in your height.
Yes. Okay, so I know that there are 2 times. Once on the way up, once on the way down. So I want to know what these 2 times are when the height is 256. Right? So I want to know when is height 256. Okay, so what I'm going to do is take my height equation and set it equal to 256. Hey, how am I going to solve that equation? Subtract 256. Ooh, hang on, let's think about that. Should we collect everything on the left or right? I think I'd collect it on the left so that the t squared will be positive. That's, for me, that would be easier if that lead coefficient was positive. Okay, why am I collecting it all on one side? It is a quadratic equation. I'm going to try to factor this booger, but I don't know if it factors or not. We'll see. But if it doesn't, then I'll have to use quadratic formula. Is there a number that will divide into all of those?
Yes.
Oh, we're so lucky. Okay. I'm going to divide everything by 16. And that will become t squared minus 10t plus 16 equals 0. Oh, does it factor? 8 and 2, right? And we should expect to be getting 2 positive numbers for t. So t is 8 and t is 2. Okay, so I still haven't answered the question. What is the velocity on the way up when it reaches this height? All I have figured out so far is that it's at this height at 2 seconds, and it's at the height again at 8 seconds. How do I find the velocity at 2 seconds? Plug it into our velocity equation. Okay, so I'm going to find velocity at 2. Go to that velocity equation. 160 minus 32 times 2. Okay, what does that give me? 160 minus 64,
Is like 96.
96. What would my units be?
Feet per second.
Feet per second. Okay. What is the acceleration? I'm sorry, what is the speed at time equals 2? It's the absolute value of velocity. So it's still 96 feet per second. Okay, so speed and velocity on the way up are 96 feet per second. Speed is still a distance per time. Okay, now let's deal with on the way down. So I want to find the velocity at 8 seconds. What should we expect the velocity to be on the way down? Negative, because that's a negative direction. 160 minus 32 times 8. Negative 96 feet per second. So that makes sense because we're coming down, negative direction. But the speed is what? Just 96. Because speed is the absolute value of velocity. Okay. Question? Okay. What is the acceleration of the rock at any time during its flight? Yes, acceleration is the derivative of velocity. So acceleration is v prime of t. Okay, well here's our velocity equation up here. What is that derivative? Negative 32. What would the units be? It's feet per second, so feet per second squared. Does that number ring a bell? Gravity. So the acceleration is just what gravity is. When is the rock speeding up and slowing down? Okay, there is a concept that we need to talk about. Okay, picture the rock going up. Is that positive or negative velocity? Positive velocity. But what is gravity doing?
It's still pushing it down.
It's pulling it back down, right? They are working against each other. Velocity is positive here. Positive velocity. Okay, over here I have negative velocity because it is going in a negative direction. Okay, but the whole time gravity is pulling it down, right? If velocity is positive, but gravity is working against it, am I speeding up or slowing down? Think about what I do at the top there. I stop. What do you have to do before you stop? Slow down. So velocity is positive, but acceleration is negative. They are working against each other. I am slowing down. Slowing down. If I turn the corner and I start to head back down towards the ground, then this is a negative velocity, negative direction, down. But gravity is pulling it in that same direction, then they are both working together, and I am speeding up. Okay? So, let's make a little note down here. When velocity and acceleration have the same sign, either they're both positive or both negative, an object speeds up. When velocity and acceleration have opposite signs, one is positive, one is negative, an object slows down. Okay, so when is it speeding up and when is it slowing down? We just said it is speeding up from, for time, on what interval? 5 to 10. It is slowing down for time 0 to 5. When does the rock hit the ground? 10 seconds. We already figured that out. Okay, graph the position and the velocity functions on the same axes. Do the graph support your answers above? Okay, so we kind of already sketched the velocity, but we can do this. Let me see how much we have left. Oh, okay. I'm not going to do this on the calculator because I'm going to try to get through this next one so that we can do something cool on the calculator. Okay, so we could do that on the calculator. All right. Studying particle motion. A particle moves along a line so that its position at any time greater than or equal to 0 is given by this function right here, where S is measured in meters and T is measured in seconds. Okay, so those are our units that we'll be using. Find the displacement of the particle during the first 2 seconds. Okay, what does displacement mean? Okay, where I stopped minus where I started. Okay, so where I stopped will be my position at 2 seconds. Minus where I started is my position at 0 seconds. Does that make sense? Okay, so if I said find S of 2, I'm just plugging 2 into the S function. So 2 squared minus 4 times 2 plus 3. That is your final position minus initial 0 squared minus 4 times 0 plus 3. So final position minus initial position. Okay, and that will be my displacement. Remember, displacement can be positive, negative, or 0. It's all related to where you stopped and started. Okay, so let's see. We have 4 minus 8 plus 3. Subtract 3. So what do I get there? Negative 4. What would the units be? Meters. Just meters. So what that means is I ended up 4 meters to the left of where I started, or behind, whichever negative direction we're considering there. Find the average velocity of the particle during the first 4 seconds. Average, what does that mean? Slope formula. So I want to find my change in position over change in time. Well, my change in position will be where I was at 4 minus where I was at 0, final minus beginning, over 4 minus 0, change in time. Or you could just say 4, because 4 seconds have elapsed. Okay, so S of 4, I'm going to plug that in. 4 squared minus 4 times 4 plus 3 minus, I already know what S of 0 is, don't I? It was 3 divided by 4. 16 minus 16, 0 plus 3 minus 3, 0. And what would that unit be? Velocity. So a distance per time. Meters per second. How can I have a velocity of 0? Yeah, stopped. Okay. Find the instantaneous velocity of the particle when t is 4. Instantaneous means derivative. So v of t, okay, go back up to your position function. The derivative is 2t minus 4. And I want to evaluate that at time equals 4. 2 times 4 minus 4, 8 minus 4 is 4. Units would be meters per second because it's a velocity, it's distance per time. All right, find the acceleration at time 4. Well, acceleration is the derivative of velocity. Acceleration will be 2. 2 what? Just 2. 2 meters per second squared. The fact that I don't have a variable here means that acceleration is constant. It doesn't matter if it's at time 4, time 8, time 400, the acceleration will be 2. Okay? So A of 4 equals 2. Describe the motion of the particle. Okay, we're going to look at it on a calculator because we're starting to run a little close. So we're going to use a parametric graph to see the motion of this particle. Okay, so get a graphing calculator. I think it's just doing this. All right, go to mode. And go to parametric instead of function. Right there. Okay, so parametric is when two variables are dependent on a third. So if I think of this as having horizontal and vertical distance or change, and those are all related to time, that's a parametric situation. So two variables are dependent on a third. Okay, so we're going to go to y equals now. Oh, notice some weird things. Okay, so see how it has x sub t, y sub t. That's your two variables that are dependent on time. Okay, so we are going to set these up. I've got it written in your notes here. I'm going to use the position function. Notice when you push the x button, it gives you time. So using the position function for the first x equation. So that's just straight up, what's the position of the object? Okay, I'm also going to go to y and use y equals 2. It's written a little bit above there, so we're going to use y equals 2. Now, the reason I'm going to use y equals 2, if I didn't use this y equals 2, then the particle would be moving on the x-axis and it'd be hard to see. So I'm just shifting it up 2 so that we can see it. You could use anything that's not 0 so that it would move it away from the x-axis. Okay, now we're going to go to our window. Okay, so t min and max, t is time, right? So we're going to use a minimum t value of 0 right here on the bottom line of what I have typed in here, time 0 to time 10. Okay, so what would be a good step? Maybe 1. Okay, x min, that's the first set of brackets, -5 to +5. Good scale would be 1. And then the second set of brackets here are the y min and max. So -2 to 4, scale of 1 will work. Okay, so my two equations were y equals 2 and the position. Ooh, y'all. Yeah, okay, there it is. I wrote it again. I didn't realize that. And then we set up our window based on what time span we want to see. All right, let's see what happens. Wow, did you see that? No, it went too fast. Okay, so let's go back to window and take our time step and make it like maybe 0.1. And basically what it'll do is like do slow-mo. Okay, that was still a little bit fast, wasn't it? And I don't like that it graphed a line. Do you remember, go back to y equals, arrow all the way over. Do you remember seeing the different things that it would use, like the little, like use the ball one. Right there. Yeah, and then it takes forever. Okay, now graph. Oh, that's a little bit better. Isn't that cool? So when you were saying model it, this actually models it. Oh, I'm still trying. Did you do a really small time step? If you do a really small time step, it'll take forever. Okay, so come on, graph for me. It won't graph again. Won't do it again. I know, it's like, duh, we already did it. Okay, let me change one thing. I'll change this to an 11. Now it'll have to graph again. Okay, so as it graphs this time, notice it slowing down before it stops and then turning around. Because like we said, your velocity, if it's going to reach 0, it's got to slow down to get there. So it slows down, stops, and then goes in the other direction. Okay? So that's the way that you can use your calculator to model some motion. If you take some higher math classes in college, you will deal with parametrics a lot more. But that's just, I think that's a cool thing to see. It's still graphing? Oh my gosh. Okay, one more thing, we can do it. Okay, have you all had econ?
Yes.
Have you all talked about marginal?
Yes.
Awesome. Okay, did you know that's really a derivative?
I did not know because I did not know what a derivative
It is, I know, that's true, you did not. So, economists have a special term that they use for rates of change, which is a derivative. They call them marginals. So marginal is their term for derivative rate of change. If the cost of production C of x is a function of x, the number of items produced, the marginal cost of production is the rate of change of cost with respect to the level of production. So it's dc dx. Sometimes the marginal cost of production is loosely defined to be the extra cost of producing one more unit. If the revenue R of x is a function of x, the number of items sold, the marginal revenue of production is the rate of change of revenue with respect to the level of sales, so it is dr dx. Okay, we are not going to get into the economics of this all. We are going to treat it just like a regular math problem and find the derivative. So, if you are given a cost function and you are asked to all right, here's C of x to produce x radiators when 8 to 10 radiators are produced. R of x is revenue for selling x radiators. Your shop currently produces 10 radiators a day. Find the marginal cost and marginal revenue. If you see marginal cost, marginal revenue, you think derivative. Okay? So for marginal cost, we are going to find C prime of x. So the rate that the cost is changing. Okay, so I'm going to go up to this derivative for cost. 3x squared minus 12x plus 15. That is the rate that cost is changing. In this situation, it would be radiators per day. Okay, let's find down here our marginal revenue. Okay, so this would be the rate that the revenue is changing, or R prime of x. 3x squared minus 6x plus 12. And that would also be revenue would be in dollars per day. Dollars per radiator, my bad, because we're producing radiators. Okay, then if I wanted the marginal cost when I'm producing 10, I would find C prime of 10. So, okay, this moment I'm producing 10 radiators a day. How is my cost changing? So let's find C prime of 10. Okay, 195. Okay, so cost is in dollars, right? Per, what am I producing? Radiators. Is it a good thing that my cost is positive? That the rate of change is positive? Not necessarily. That means that when I'm producing 10 per radiator, it's costing me almost $200 more per radiator. It's positive. What if it was negative? That'd be good news. It means my cost is coming down. Okay, well, let's see what the revenue is when we're selling 10 or making 10 a day. I'm going to plug 10 into my rate of change of revenue. Revenue is the money I'm bringing in. That's a good thing, right? Okay. Okay, well, that's positive, so that's good. It's $252 per radiator. Okay, so at least my revenue is staying ahead of my cost, which is a good thing, right? And my revenue is positive, which means the revenue is increasing. It's a rate of increase. Okay, I would definitely not want that to be a negative. Okay? All right, so that's the extent of our econ in here, our econ lesson. Just when you hear marginal, think rate of change, think derivative.
So I'm assuming buyers are going to enter the market right now.
On the radiators?
Yeah.
Yeah, go invest in radiators today.
And then a couple months later, they're going to be in the long run, and then they're